Good evening, everyone. Myself Anshul Singh. So I will be your TA for this course. I am a PhD student at ICER department, that is Interdisciplinary Center for Energy Research Department at ISC Bangalore. So currently we have been doing the course of power quality offered by Professor Bhim Singh from IIT Delhi, and so far we have discussed about the topic of power quality. What is power quality? What is the need for power quality? And what are the power quality problems that are present in our electrical grid. They were current based power quality problems, voltage based power quality problems. Then after that we started going ahead with improvement of power quality. How can we improve? So first we started with passive compensators. We started talking about passive compensators, which is a combination of passive components like inductors, capacitors, resistors that provide fixed kind of compensation. So initially we were able to do with fixed kind of compensation, but now since our the nature of our load is changing with time, the load is not anymore a fixed kind of load because of the presence of power electronic based low electrical loads, and due to presence of loads like electric vehicles and a lot of dynamics involved in the load, we are switching to active compensators now. Active compensators is passive components plus switches. So with active compensation, we are dynamically able to change the reactive power or the active power that is injected by our loads. So now when we talked about active compensation, we discussed about the current compensators just focusing on current power quality problem, that is called D-statcom. Then we focused on active series compensator that focuses only on voltage power quality problems, and that was called DVR, that is dynamic voltage restorer. And then now today we are going to discuss about UPQC, that is Unified Power Quality Compensator. And in UPQC is a combination of both shunt and series active compensators. That is UPQC has the features of doing both series and shunt compensation. That is UPQC can take care of both current and voltage power quality problems. So today we are going to discuss about the lectures that were allotted to you in this week, and after that we'll be solving few numerical problems. Okay, so we'll start with our theoretical revision of what has been taught in the previous week. Okay, so let's get started. So UPQC is a combination of, as I mentioned, UPQC is a combination of both active series compensator and active shunt compensator. Now, because it has both the components, it is able to take care of both voltage power quality problems and current power quality problems. Now, as you can see, this is a schematic diagram of UPQC. So this is our traditional electrical grid, this is our electrical load, and then there is series compensator, and then there is shunt compensator. So both of them are connected together forms the UPQC. So this is our total UPQC, which has both series compensator and shunt compensator. That is, we can call it, this is DVR, this is D-statcom, and both DVR and D-statcom together forms our UPQC. So because of the presence of series compensator, our load is able to get balanced voltage at its load end. And because of the presence of shunt compensator, our source current is beautifully balanced, even though our load current is unbalanced and non-linear. So this is the advantage of using a UPQC kind of compensator. Now let us talk about the classification of UPQC. So when it comes to classification of UPQC, the classification is based on multiple bases. One of the bases is based on the type of converter. Another basis is based on the topology, and apart from that, the classification could be done on the basis of the supply system. So these are the three classifications. Then, based on the converter type, we already have been discussing this continuously, that based on the type of converter, UPQC can be classified as current source converter or voltage source converter. Then, based on the topology configuration, UPQC can be classified as right hand shunt UPQC and left hand shunt UPQC. This right and left we'll be discussing when we go further. So now when we talk about classification based on the supply systems, we again have seen the conventional ones, which is based on two wire, three wire, and four wire. Another classification is based on the method of control. So this same hardware configuration can be controlled in multiple ways. And when we are controlling it, we could either control it in the mode called UPQC-Q, where only reactive power is controlled, or UPQC-P, where only active power is controlled, or UPQC-S, where both active and reactive power components are being controlled. So based on which type of mode we are operating, the rating of our UPQC compensator will change because its operation is changing. And based on these operations, the rating will also vary. Now, as we talked about the classification based on the type of converter, if we use voltage source converter, a converter will look something like this. This is a general diagram. Similarly, if I use a current source converter, my compensator will look something like this. Now, when the reason we have already discussed this before, the reason why we use voltage source converter more than current source converter is that the DC link capacitor that is present in the voltage source converter is comparatively cost effective, and since the switches that are used in this pattern at a time only one of them is conducting, therefore conduction losses at a time are either corresponding to the switch or corresponding to a diode. Whereas when we talk about current source converter, since the devices are connected in series, the conduction losses are corresponding to both the switch and the diode at the same point of time, as a result of which our conduction losses increases. Similarly, this inductor is which is present, which is a connection between the two DVR and the D STATCOM. This inductor has to be a DC inductor, and as you know that inductor has a capability of getting saturated because of its material properties. So what we do is we introduce an air gap in order to make it a DC inductor, which is very bulky in size and it is highly lossy in nature because of the presence of the air gap. And also there is the need of these additional capacitors in this circuitry. So because of these problems, this current source based converter is a very lossy converter, and it's overpriced compared to a voltage source converter. That is the reason why most of the topologies that are present in the market are based on voltage source converters. Now let us discuss about the right hand and left hand shunt UPQCs. So when we talk about right hand shunt UPQC, the right and the left are the positions of the D STATCOM in the UPQC. So when I say right hand shunt UPQC, that means my D STATCOM is present on the right hand side. And when I say left hand UPQC, then my D STATCOM is present on the left hand side. Then my D STATCOM is present on the left hand side of the UPQC. So, the right hand shunt UPQC and left hand shunt UPQC have only one feature that is different, that is the placement of DStatCom. Now, let us see what is the effect of moving these DStatCom from right to left. So, when you look at the configuration of right hand UPQC, since my DStatCom is present near to the load, it is already compensating for my load current. Therefore, the current which is flowing through the DVR is is only the good part of current. As a result of which, what is happening is the current which is flowing to the DVR, since it is good part of current, that as a result of that, the rating of my DVR is reduced. Similarly, because my DVR is present at this point, the voltage that appears across the D STATCOM terminals is a good quality voltage. As a result of which, the rating of my D STATCOM reduces. So, in right hand shunt type of UPQC, the rating of my overall UPQC is reduced because of just what I just mentioned. That because of the reduction in rating of DVR and in the rating of DStatCom, my overall rating of UPQC reduces. That is why right hand shunt UPQC is the most popular kind of UPQC that is actually used in our distribution system. Whereas when we talk about transmission system, in transmission system, what happens is these DStatComs are present on the substation, whereas DVRs or the voltage control devices are present in the transmission lines between at some distance. And the reason of doing that is because in transmission line, in order to improve the power transmission capability of your transmission line, we use series. We have discussed in the very start of the lectures that series kinds of compensators are mostly used in transmission line because they help improve the power transfer capability of the transmission line. Whereas when we talk about distribution, since the nature of load is highly fluctuating in nature, we usually don't go for series voltage kind of devices in distribution system. Therefore, these left-hand type of configurations are mostly used in transmission systems. And as you can see here, that since DVR is placed after D-STATCOM, that means the current that will flow through the D-STATCOM will have the bad component inside it. As a result of that, the current rating of DVR will increase, as a result of which the uh, overall rating of the UPQC will increase. So this is the reason why in distribution system mostly right hand shunt UPQCs are used instead of left hand shunt UPQCs. Now, this is one of the sample examples of single phase left shunt UPQC. Now, since it's left shunt, D-STATCOM will be present on the left hand side. And as mentioned, this is our D-STATCOM and our DVR will be on the right hand side. Similarly, in case of right shunt UPQC, our D-STATCOM is present on the right hand side. So you can understand the significance of them. Okay. And in most of the places, if you are if you have to answer which is the most common kind of UPVC that is present, that is right shunt. Because in distribution system, when we talk about, we mostly go for right shunt because of reduced ratings. Now, this is an example of three-phase right shunt UPQC. In three-phase right shunt UPQC, the voltage source converter could be either a three-leg converter or a four-leg converter. So it depends on our application whether you are attempting the neutral current compensation there or not. So if you are attempting neutral current compensation over there, then you will have to use a four-leg converter like this one. This is a four-leg converter for neutral current compensation, whereas this is a three-leg converter. Three-leg, the only problem with three-leg compensator is that it is incapable of taking care of neutral current. So this was our right shunt UPQC for three-phase configurations. Now, let us discuss about the methods of control. As I mentioned that UPQC2 is UPQC-Q is a type of UPQC that can supply only reactive power, and UPQC-P is a type of UPQC that can supply only active power. And if you need your UPQC to supply both active and reactive power, then it is called UPQC-S. So, so depending on what goal we are trying to achieve, our method of control is going to change. So our application will tell us the need of which kind of UPQC, and then based on that we will select whether we want to go for UPQC Q, P, or S. Now let us discuss about UPQC Q in a bit detail. In UPQC Q, the shunt compensator is normally connected across the consumer load, and it will mostly be in right side shunt UPQC as we just discussed. And this D-STATCOM is used for all current based power quality problems, and DVR is used for all voltage based power quality problems. Now, since we are saying that it is a Q type of UPQC, so we can say since it is going to deal only in reactive power, that means that DVR will be dealing only with reactive power. So this Q rating is the rating of the DVR. And when we say UPQC-P, that P will tell that the DVR in that UPQC will deal only with active power. So this is a structure. This is the circuit diagram of UPQC-Q. This is again a single phase circuit, and it is right shunt because the STATCOM is present on the right hand side. Now, let us look at the phasor diagrams. So, most of the problems that we'll be dealing with will have their basis from the phasor diagrams. So, when you look at this phasor diagram, suppose the voltage reduces. Suppose there is a problem of voltage sag, and this is my standard level where I want. Then, if my voltage has reduced to some level, then using UPQCQ, I can just add VDVR in at an angle of 90 degrees because it can supply only reactive power. So by adding quadrature component, I can compensate for voltage sag problem. Whereas if you see that if in case my voltage exceeds beyond the level what I want, then by doing then using the DVR, I am unable to compensate for the voltage swell condition. Here, here my voltage, if Vs dash was my voltage, which is the swelled up voltage. Now I want to reduce Vs dash in such a way that it it lies within it the arrow of the my load voltage vector lies on this arc. I'm not able to do that because it is a UPQC-Q type of UPQC where only voltage can be added in quadrature. And because of that, we say that UPQC-Q cannot be used for voltage swell compensation. It can only be used for voltage sag compensation. Okay. Now let us talk about UPQC-P. So UPQC-P, the only difference is that here DVR can inject only active power without any reactive power injection. So since it is injecting active power, we have to think about the maintaining minimum voltage injection across it. So in this UPQCP, the rating of the DVR is quite low because we are working on minimum voltage injection. So if you look at the phasor diagram of UPQCP, since it can inject only active power, that means it can inject only power in phase with the source voltage. So it could either be in phase or it could be in opposite phase. So this is the only two possibilities with UPQCP. But we can say that with using UPQCP, we are able to solve the problem of both voltage sag and voltage swell. Now let us talk about UPQC-S. So UPQC-S is a kind of UPQC that can deal with both active and reactive power. So UPQC-S, in UPQC-S, the dynamic voltage restorer injects both voltage in series and it can inject both active and reactive power with the minimum VA rating of both VSCs and other criteria. So when we talk about minimum VA rating, the main motivation behind the minimum VA rating is the cost. So when you want to reduce the cost of any kind of, why would I pay 100 rupees for a thing that I can get for 50 rupees? If I can make the same thing in 50 rupees, I will definitely make it for 15 rupees, right? So that is the purpose. So therefore, we always try to reduce the rating as much as possible. Okay. So therefore, the compensator which can solve my problem with minimum VA rating, that means at the cheapest rate, I am going to pick that compensator. In this type of UPQC, the ratings of both DVR and DStatCom are minimized or utilized in proper coordination to supply reactive power of the system with proper sharing. So when we talk about UPQC-S, since we can supply both active and reactive power, now the VDVR vector or the voltage vector of the DVR could be at any angle. So I can compensate for both voltage and voltage swell in any condition. So I could get any kind of power angle delta between VS dash and VL dash using VDVR. Okay, so this is the most what we can say. It is the device that can cover a huge range of operation. UPQCS. So whenever you have a load that is very generic in nature and you don't know what kind of behavior it is going to have, then you can just pick UPQCS. Now let us look at the principle of operation of these UPQCs. So as we know that they have two voltage source converters. One is connected in series, another is connected in shunt, and the series one is called as DVR, that is dynamic voltage restorer, and the shunt one is known as DStatCom. Both these voltage source converters are pulse width modulation controlled, and they have Hall effect based voltage and current sensors, and they have DSP boards for implementing their control algorithms. Now, the important part is since DVR is the purpose of DVR is to control voltage, therefore DVR operates in voltage control mode. And DStatCom, the purpose of DStatCom is to improve current power quality problems. Therefore, it operates in current control mode. Okay, so you need to take care of this thing in. And when we need to design, then there are a lot of passive elements. There are DC bus capacitors. So it's like designing of UPQC is like designing both DVR and DStatCom simultaneously. The only difference is if you are designing both DVR and DStatCom separately, then you will have two DC link there. Whereas if you are designing in UPQC form, they share a DC link. So because of the presence of this common capacitor, uh, the need for another capacitor is reduced. Otherwise, everything else is same. Okay, so we will be using all the concepts that we have discussed so far. Now, for the design of three-phase four-wire UPQC, let us look at what are the things that we need to design and how do we design it. So this is an example of three-phase four-wire UPQC where DVR will have three legs and DStatCom will have four legs with a capacitor uh, that is being shared between both the DVR and DStatCom. Now, if you look at the design of three-phase four-wire UPQC, it includes the design of DStatCom and DVR separately. So, when we talk about the design of DStatCom, we have already done this. We have designed the voltage rating, current rating, the kVA rating, the DC bus voltage, and the DC bus capacitance, and the AC interface inductor, and the ripple filter. Similarly, for the DVR, we have done the same thing. We found out the voltage rating, current rating, kVA rating, and injection transformer rating because it is providing isolation there. Then DC bus voltage and DC capacitors along with AC interfacing inductance and ripple filter. So when both all these components basically when you design both DVR and DStatCom individually, it's almost similar to designing a UPQC. Now let us take an example of designing of UPQC. So they have considered a numerical example instead of taking a generic equations. So using the example, you can understand. Let us assume that we have to carry a design of UPQC P, where the supply system has IC line voltage of 415 volts 50 hertz with the voltage variation that is plus minus 30 volts. That means it could either have a voltage swell of plus 30% or it could have a voltage sag of minus 30%. And the line impedance is given as zero point 0.1 ohms and LS is 1 millihenry. And the nature of load is three-phase four-wire load, 30 kilowatt, zero point 0.8 power factor. So the D-STATCOM voltage source converter is designed for compensating a reactive power of load, which is 22.5 kVAr. So active power is 30 into zero point 0.8 and reactive power is 30 into zero point 0.6, that is 22.5 kVAr. Okay. So we know that the D-STATCOM rating is 22.5 kVAr because the load, that is what the load needs. And let us assume that the allowable ripple in VDC, D-STATCOM current and the AC mains current is given as 5%, 15%, 10% respectively. And let us assume that the switching frequency that we are considering is 10 kilohertz. Then let us start with the design of DC bus voltage. Then we know that VDC is equals to 2 times the maximum voltage at the point of common coupling. So if line to line voltage is given by root 3, we can find out the phase voltage, and phase voltage into root 2 will give me the maximum voltage, and twice of this maximum voltage will give me the DC link voltage. So this is what we calculate, and then we will take the value which is near to it, which is 700 volts. Now, let us look at the value, the selection of DC bus capacitor. Again, we have done the energy conservation. Half CV square is equals to the transient power that we need to supply during any kind of transient faults or load or transient condition. So that is this equation. And based on this, we can find the value of capacitor and we'll take the nearest value which is available, that is 3500 microfarads. Now, let us focus on the selection of AC inductor. So when we talk about the selection of AC inductor, we have already used these formulas before. Again, you can just put the values in these and we know what all these values mean. We know the overloading factor, the switching frequency, the ripple current. We have already discussed that. So I won't spend much time on these things again. And similarly, as we know the current, since the current maximum current to neutral wire changes, therefore the inductor equation for the neutral leg also changes. And based on this equation, we can calculate the inductance needed to connect in the fourth leg, that is the neutral leg of our compensator. Now, if we talk about the design of the ripple filter, we have discussed this before that ripple filter is supposed to absorb the switching frequency components. Therefore, we design it in such a way that it takes care of frequency components which are above 5 kilohertz because we have 10 kilohertz switching frequency. So let us assume that I am taking the 10th of that. That means whatever is my switching frequency, I am considering to filter the voltages 10 times more than that. So if you look at filtering of those voltages, yes. So if you look at filtering of those voltages, then you can see that for fundamental frequency component, we need to design this. We need to select this RF and CF in such a way that the impedance offered for designing the impedance offered towards fundamental frequency component is high, and the impedance offered towards switching frequency component is low, because when my ripple filter is connected in shunt, I want my fundamental component to go as it is. I don't want my fundamental component to flow through it. And when my switching current component is flowing, I want it to offer low impedance so that all the switching current flows through this path. And my load, which is connected here, is unaffected by the switching current. Therefore, we want the to offer impedance value to be low for high frequency component 10 kilohertz and high for low frequency component, that is our 50 kilohertz. Sorry, 50 hertz. Okay, so we can choose any value of RF and CF. Okay, and this is just a engineer's judgment. You could use any other value as well. Now, we can similarly, based on the values, we can calculate the losses in the ripple filter. We know that the current in the ripple filter is the phase voltage divided by the impedance, and during the high frequency, for the high frequency components, we could calculate the value of current, and then the losses, and then the losses at fundamental frequency can be found out in this way, 3I square R. Okay. Now, let us discuss about the voltage rating of the solid state switches. So, as we have already discussed before, that the switch rating in these 4-leg or 3-leg converter depends on the DC link voltage and the tolerance. If I am considering my DC link voltage to be to maximum go up to 10% of its full value, then I can calculate my switch rating as 700 plus 10% of 700. So it will come out to be 770. And since there are only few ratings that are available in market for these standard switches, so the nearest to that is 1200 volts after considering the factor of safety. Similarly, we have seen the similar equation for current, where I will have the peak to peak value of current and the ripple current, and 1.25 is the safety factor. So using these values, we could calculate the value of the current, and we could pick an IGBT or any other switch that has current rating more than what we just calculated here. Similarly, now let us so far we were designing D STATCOM. Now let us move on to the design of DVR. So in DVR, we know that there is an injection transformer, and since we are considering that the maximum sag or swell that is going to occur in our voltages plus minus 30%. So my DVR will have to inject a maximum of 30% of the phase voltage, right? This is the maximum voltage that my DVR will have to give to the grid, because I have already constrained that because any device that you design have to given certain specifications, right? It cannot be made for 100% 100% compensation, otherwise its price and its rating will increase, right? So they take this constraint, and based on that we design. So the voltage rating of the DVR is the 30% of the maximum voltage that you want at the point of common coupling. Now, when you talk about the maximum turns ratio, so we know that this turns ratio on one side we have to give 71.88 volt, and on the other side this should be corresponding to the phase voltage, that is 415 by root 3. So when we divide this phase voltage by this voltage, what we have, we obtain the turns ratio of the transformer. Okay. Now, when we talk about the voltage rating, VA
Generally, you are
rating.
selecting
Uh,
generally here you are selecting general value more than 3 and 4 you have to select, madam. But why you written 3, madam?
yes,
Generally
yes, yes. Normally, so this is the
3.3.
maximum value. So since this is the maximum value of turns ratio. That is why I think they have taken less than 3.
Okay, okay.
Okay. So you can take 4. Like it's always good to
Okay,
have
okay, okay,
more.
madam.
Yes,
Okay.
yes. So the VA rating of the injection
Okay, okay.
transformer we can obtain from the product of its respective voltage and current ratings. And in order to obtain the current rating of the DVR, it will be maximum when the voltage will be minimum. So minimum voltage we know it's minus 30%. That is 0.7% of the phase voltage, right? So if we want maximum current that my DVR has to supply, it will be corresponding to the minimum value of phase voltage. Now let us look at the design of interfacing inductor for the voltage source converter of the DVR. So so now when we talk about inductor of DVR, so it is inversely proportional to the ripple in the DVR current rating. So for maximum value of inductor, I need the minimum value of my DVR current. In order to calculate the minimum value of my DVR current, it will be corresponding to the situation when I have a voltage swell. When this will be maximum, my current will be minimum. And when my current will be minimum, my inductor value will be maximum. So the goal of my designing interface inductor is to calculate maximum value of inductor that I need for my circuit. And that will be corresponding to a situation when voltage swell occurs. So therefore, I am considering this here. So this is 1 plus x is nothing but uh, the factor that will give me voltage swell condition. So x is my zero point 0.3. So during voltage swell, my voltage will be 1.3 times 239.6. So that is what this is representing here. Okay, and since it's a three-phase circuit, so it's 3 times the voltage. So using that, I can calculate the inductor value of my DVR for interfacing with the at the point of common coupling. Similarly, for calculation of the device rating, the voltage rating of the DVR device is same as that of D-STATCOM because both share the common DC link. So it will so based on the turns ratio of the DVR that we had just obtained, and since we want the maximum current rating now, so we need to have the maximum value of DVR, and that is under the SAC condition. When voltage is minimum, current is maximum, right? So again, this is the SAC current expression, and then NDVR we just calculated. Okay, and the ripple filter design is again the same. We have to take care of the switching frequency components. So we can select the value of R and C in such a way that it offers low impedance to the high frequency components and high impedance to the low frequency components. So we just have to take care of that part. Now let us look at the control of UPQC. So as we discussed before, there are a lot of methods involved for controlling the UPQC. Then the methods are divided into two broad categories. One is time domain control algorithms, and another one is voltage frequency domain control algorithms. And as we have already discussed before that since in frequency domain, what happens is the we first have to transform the time domain signals into frequency domain and then do the computation process. Whereas in time domain control algorithms, we already have signals in time domain and we just have to do the computation part. So since an additional step is involved in frequency domain control algorithms, therefore we are unable to do it quickly. And since my grid frequency cycle is 20 milliseconds, that is corresponding to 50 hertz. Since my frequency cycle is very fast, so I need to act fast for dynamic compensation. And since I need fast acting, therefore, mostly time domain control algorithms are preferred compared to frequency domain control algorithms. Okay. But nowadays, recently, since DSPs and all the all the controllers or the processors that are available in the market are able to operate at a very high frequency. The clock frequency that are available in market are around megahertz range, 200 to 100 megahertz. So because of that high frequency availability, nowadays people have started using frequency domain control algorithms as well. So few examples of time domain control algorithms are synchronous reference frame based control algorithms, then unit template technique. We have seen a brief about almost all these techniques before. Then another one is instantaneous reactive power theory, instantaneous symmetrical component theory, and neural network theory, then single phase PQ theory, single phase DQ theory, etc. And then there is enhanced PLL, that is enhanced phase lock loop based control algorithm. And the recent ones are adaptive algorithms, that is adaptive detecting algorithm, also known as adaptive interference cancelling theories. And these are only few examples. In the literature, there are more than 1,000 algorithms that are already present. Then when we talk about frequency domain control algorithms, there is Fourier series theory, discrete Fourier transform theory, fast Fourier transform theory, recursive DFT, Kalman filter. This is one of the most popular ones. It is used in space technologies as well nowadays. Wavelet transformation theory, Stockwell transformation theory, empirical decomposition transformation theory, Hilbert-Wong transformation, and these are just again few examples. In literature, thousands and thousands of these are present. Now, let us look at the control of UPQC. Let us say we are discussing about UPQC queue. So in the control mode, we know that Q means DVR is mainly used for giving reactive power to the system. It will inject only reactive power, and uh, and we also have seen that UPQC-Q is capable of taking care of only voltage sag problem, not the voltage swell problem. And in this case, the purpose of DStatCom is to do unity power factor correction, and DVR is in charge of taking care of the voltage regulation. In this case, voltage sag compensation. Also, there is limitation of sag compensation depending on the voltage rating of the DVR. So this is the phasor that we had already looked at. That using because of this phasor, we know that UPQC-Q is not able to take care of voltage swell. It can only take care of voltage sag. Now, if we look at the equations, so X is basically the percentage sag or swell. Okay. So in order to calculate X, you can use this equation because the voltage injection, because all three are at right angle, right? So it's just Pythagoras theorem. Okay. So using Pythagoras theorem, you could obtain this equation. X is normally given in the question, so usually you won't have to calculate it. Okay. This is just a way the sag parameter is defined. Okay. So when you say 20% reduction, that means this X is 0.2. Okay. Now the rating calculation for both DVR and DStatCom can be easily understood from the phasor diagram. Since it's a right angle triangle, we could say that VDVR plus V source is equals to V load, right? Square, sorry. V source square plus VDVR square is equals to V load square. It's Pythagoras theorem. So from that, we could get VDVR or V injected voltage as this. Similarly, since we know the source current rating of the supply, and the volt ampere rating of the or of the injected voltage or the DVR, the product of two will give us the apparent power of the DVR. Now, this IS is equals to IL cos phi into tan delta. This expression comes because this current depends on D statcom. Okay, and this tan delta is defined as this. And in order to calculate the current rating of the D statcom, this is the expression that we will be using. So in this class, I was unable to cover the derivation, but if you guys need, then I can take care of these. I can tell you the brief about these derivations if you want. So you can let me know if you want to learn the derivations as well. And then since we have got the current rating of the DStatCom and the voltage rating we already know from the DVR, so we could just calculate the VA rating of the DStatCom. And the combined rating of the UPKC is the sum of the rating of both DVR and DStatCom. Okay. Now let us look at the design of UPQC-P. Now we know that since it is UPQC-P, it DVR needs only active, can inject only active power. Yes. So the UPQC-P is responsible for, it increases the current and thus the kVA rating of the DStatCom. However, the kV rating of the DVR is minimum in this case. And also we had just seen that it can compensate for both active and reactive power. But it can it can inject voltage only in phase, right? This was the phasor we had just looked before. So when you look at the equations of this kind of UPQCP, then we could directly subtract or add these values. We don't have to take care of any kind of phasors or uh, the square root that was present in the maximum complicated or generic case will come for UPQCS, because there DVR can be present at any angle. So we will have to take care of the angle there. That here we know that it is either in phase or in opposite phase. So X can be defined as this. That is the difference between the load and source voltage and the ratio with respect to the load voltage that we desire. So X is again our percentage lag or lag or lag me sorry sag or swell, sorry. Hmm. Now we know that the injected voltage by the DVR is can be directly put as the difference between the two, because it is very clear from the phasor, since we are just putting the DVR voltage in phase or out of phase. So we can just obtain it using this expression. Similarly, the voltage, the VA rating can be obtained as the injected voltage into current, and the supply current can be obtained from the D statcom. Okay. So since we are dealing only, since D statcom is giving only active power in this case, therefore it will be D statcom will be supplying only the good part of the current. So sorry, it will be supplying the bad part of the current, and therefore the source current after application of D statcom will be I cos phi. Okay, so this is the IS value here. Now that we have just seen that the D statcom current is this expression, because D statcom has to supply both active and reactive part of the current. So it is sum of both of those currents. Okay, we'll see this in a problem as well. So when we just multiply the voltage rating of the DVR and the current rating of the D statcom, we get the VA rating of the D statcom. And again, the VA rating of the UPQC is sum of the VA ratings of DVR and D statcom individually. Now let us look at the design of UPQC-S. UPQC-S, we have seen that has been featured as most generalized one. As I mentioned, that it is the most generalized because here the voltage vector can be added at any angle, and with a number of, it can fulfill a number of objectives. Few of them are the overall minimum VA of both D statcom and DVR is least. The sum of VAs of both DVR and D statcom is minimum in this one, and both DVR and D statcom are fully utilized. There is optimum sharing of rating between the both DVR and D statcom. So when you design, so when you have a problem statement and you try to design all three of them, UPQC Q, P, and S, then you will observe that there is perfect sharing and optimized rating between UPQC S. So in UPQC S, the DVR may inject voltages for both conditions of voltage sag and swell. In the UPQC S mode of operation of UPQC, the D statcom is normally used for all current-based compensation other than full reactive power of the system. So if you look at the phasor diagram, as I mentioned in UPQCS, this VDVR component can be in any phase. So here you can see it's not just 90-degree or just in phase. It can be any angle. So this is just one example given here. So depending on whether you are trying to achieve sag problem or swell problem, it will be able to solve it. So this is the most generic one. And as I mentioned that here you will have to take care of the angle at which the VDVR is present. So if you do proper calculations using geometry in the phasor diagram, then you will be able to obtain. So as you can see in this diagram, VDVR, this is VDVR vector, and the angle that it is making with the VS voltage is psi. So this psi angle can be given by this equation. Okay, so this is what we are calculating using this. So there you can draw this and understand the derivation of this. But in case you are not interested, you can just use this equation directly. Okay. Now, since we know now the angle psi and we know VDVR, we know that the active power of the DVR is VDVR into IS into cos phi, and the reactive power of the DVI will be VDVR into IS into sin phi. Okay. It's just again vector geometry. This is psi This is VDVR and this is VS. So the active component will be in phase component and the reactive component will be quadrature component. So in phase component is cos phi component and quadrature component is sin phi component. So this condition of DVR is considered for the compensation by DVR with minimum active power and maximum reactive power, full utilization of its rating. So therefore, VDVR is considered as VR. So VA rating can be directly written as VDVR into IS. Now, let us talk about the D-STATCOM part of it. So we know that in order to calculate the D-STATCOM current, we have this expression, including both active part of current and the reactive part of current. Now, this D-STATCOM needs me to calculate the value of beta, phi, and x is already known. So in order to calculate angle beta, we need angle delta, and angle delta is given by this expression in this. So these all expressions are coming from the phasor diagram. So if you look at the phasor diagram in detail, then you will be able to obtain these equations. And in case you are interested to know about the derivation, again, you can let me know. We can take this up in one of the classes. So this is given as the equation of psi that we had just seen above. So based on this value of psi and IDST, we can calculate the active component of the D-STATCOM and the reactive component of the D-STATCOM. Now, the overall apparent power of the D-STATCOM is just load voltage into current. And similarly, the voltage rating of the UPQC can be given as apparent power of the DVR plus apparent power of the D-STATCOM. So Sarah has just explained one kind of uh, control algorithm for the control of UPQC, and that is synchronous reference frame theory based control. So, so this is our DVR part, and this is my DStatCom part. Now, I know that my DVR part is responsible for taking care of my load voltage. So, here, my this is my load voltage that is actually present and sensed by the sensor, and this is my reference load voltage. Now, from where will I get my reference load voltage? There are two places. First is my source voltage. I have a distorted source voltage and I want a decent load voltage, and this decent load voltage will be taken care by my DVR. So I have my source voltage. Since it is synchronous reference frame theory based method, I will be converting these ABC components into DQ components. So VSABC will be converted to VSD and VSQ. And since they will be oscillating in nature, because the input source voltages are assumed to be having some unbalanced components and ripple or some non-idealities inside. Therefore, in order to obtain the DC component of the D and Q component, I am using a low pass filter here. Then I will obtain VSD DC component and VSQ DC component. Now this can be directly given as the D component for reference calculation. Whereas for Q component, I will add one more component, which is the load voltages at the point of common coupling. Now I know that if my point of common coupling voltage is not equal to the desired voltage, suppose I have a line voltage of 400 volts, then the per phase voltage should be 400 by root 3, that is 230.94 volts. So if my point of common coupling voltage is not 230.54 volts, then this loop will get activated and it will calculate the average value, what is there currently and what is the value that I want. And based on that, this loop will get activated, and this based on both of these errors, my Q component will be designed. So we have already seen like something like this before. So this is my DVR part of the circuit. So this is able to give me the the reference for the load voltage. Now, actually my DVR is controlling VDVR. There is source voltage, there is load voltage, and then there is VDVR. So I could have also have VDVR A phase references, B phase references, C phase. That is called direct voltage control. But we are doing indirect voltage control here. And the reason behind doing that is we have discussed before. The reason that we do indirect control here is because it's easier to generate these low reference load voltage values rather than reference DVR, because the reference value of DVR will vary from time to time, and it is going to have some non-linear, very high non-linear components. So it will be difficult for us to generate those, and it is easier. We know that my load voltage should be sinusoidal in nature, right? So it is a standard signal that I want to give. Whereas the reference DVR voltage would be something non-linear, which I'm not sure of. That is why I don't want to give that references. That is why we are going for indirect voltage control here. Similarly, now this is my D-STATCOM. The aim of my D-STATCOM is to take care of load current. And since my D-STATCOM has to take care of load current, what I'll be doing there is I'll be I'll be making sure that my source current is sinusoidal in nature. Again, I'll be doing a indirect current control here for the same reason, because it is easier for me to tell that my source current has to be sinusoidal in nature. It is easier for me to generate this reference than to generate the reference for compensator current, which will be highly nonlinear in nature. Okay. So therefore, I wanted to generate source current references. Now, again, I will be using my load current for generating these references, and in order to get the angle for the DQ0 transformation, I will have a PLL. The purpose of my PLL is to track my voltage to the current load current, or current value of load current, or current value of source voltage, that we have already discussed, right? It's a concept of space vector. In space vector, we try to rotate along with our signal, and if you want to rotate along with the signal, I need to know the angle, and that angle is found using the PLL. So for ABC to DQ transformation, this angle is given by the PLL. Okay, so these ILA, B, and C values are converted to ILD and ILQ using the PLL, the angle from the PLL. Now, similarly, here for the maintenance of DC link voltage, this Q component, this loop will get activated when my DC link voltage is reduced. Okay, this loop takes care of the point of common coupling voltage. This loop takes care of the DC link voltage. Then, based on these D and Q components, I can obtain the reference source current and compare them with the existing source current and generate the gating pulses for my D-STATCOM. Okay, so this will be the general schematic for almost all type of methods. The aim of any control method is to generate gating pulse for our DVR and D-STATCOM. Then the logic that we are using here is we are transforming my ABC to DQ signals, and then I am using my PI controllers. Instead, I could use any other method that we had already discussed before. Okay. Now, these are the equations that will be used. So, for ABC to DQ transformation, we'll be having our standard Park transformation matrix. Then, once we obtain this DC, this ILD, Q, and 0 components, I know that this ILD component will have both DC and AC component. In order to get rid of the AC component, I will put a low pass filter so that I can just obtain ILDC. Now, for DC link voltage control, we know that we need a reference DC voltage, and this is the measured one. Then it will give me an error. And once I pass it through a PI controller, I will be able to generate the loss component. And I will add this loss component to the D axis component. This is the loss component, and this is added to IDDC. And for power factor correction, IQ star and I0 star will be set as 0. Similarly, now I have ID star, IQ star, and I0 star. From that, using inverse Park transformation, I can obtain the reference supply currents. And using these reference supply currents, I can obtain my uh, the the gating pulses for my D-STATCOM. Now this was for the D-STATCOM design. Now for the DVR, we know that again we have supply voltages. From supply voltages, we can calculate the DQ0 components. Then again, these DQ0 components will have both DC and AC parts. I will use low pass filter to remove this AC part and just take care of the DC part. Also, I know that there is this point of common coupling voltage, and based on the error that this point of common coupling voltage has, this VQR component will be generated, and using this VQR component, I can modify the VQ star component. And using these VD star, VQ star, and V0 star, I can obtain my load reference voltages. Okay. So this was the equations that will be followed in order to implement this control algorithm here. We this what's inside this block and this block, they were the equations that we had just discussed. Okay. And why low pass filter was needed, what is the PI controller doing, all these things were explained by the equations that we had just discussed. Okay. Any doubts in the theory part of UPQC?
No, madam.
Okay. So let us move on to the numericals part for today. So I didn't get much time to prepare like the previous assignments that you guys were telling. I hope you got that problem that you had before. You were the one, right, Venkat sir, that cos theta and beta
Yes, madam.
equations.
I solved that problem, madam.
You were able to get
Uh,
it, right?
yes, I solved, madam.
Okay, okay,
Yes,
great, great,
madam.
great, great. Okay.
I
So
solved
I'll
that problem, madam. I got answer, madam.
Okay, great, sir, great. So I'll cover these
Hello.
assignment questions that you had in next class. So what I'll do is I'll try to in next class. I think we have very less theory portion. The topics of load is very simple, and I think assignment will also be simple. I haven't checked out the assignment yet, but I think it's comparatively simpler to the previous ones. So I can take some time there and I can solve the your assignment problems for static synchronous series compensator, and that is the one you found difficult, right? And apart from that, SSSC, which one assignment was difficult? So you can tell me the assignment number so that I can solve those ones.
Solved all assignments, madam. No, I got
Sorry?
every assignment 100%, madam.
Okay, okay, okay.
Madam. Hello.
Yes, yes.
Okay. I solved all problems, madam.
Okay, okay,
Assignment
okay.
problems.
Okay, so okay, you might
Okay.
not be the one who is asking. Somebody was actually asking me to solve the assignment problems. So okay, maybe I'll.
Actually, at that time, I am asking, madam, I'm not getting answer. After that, I solved minimum VA rating problems. Then I
Uh-huh.
will understand, madam, how
Yes,
will
yes.
getting that
In
answer.
lectures, actually, sir actually quickly went through those topics. But if you will focus on the solution, na, he has given all the details there.
Yes, madam. Means that directly quadratic equation getting that is the only confusion, madam. Before that, but after
Okay.
I'm getting that cos beta equal to some value, sin beta is equal to 1. After that, you have to squaring both cos square and sin square. Then you have to add then equal to 1. Then you are getting two values of ESSC. One is maximum value, one is minimum value, madam.
Okay, 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 okay. Nice, nice. Take it. Okay.
I
Then
solved that all the minimum VA rating problems, madam.
yes, the concept you understood, right? That for minimum VA rating, what all things have to be taken care. And for minimum rating, we are
Yes,
introducing active and reactive power both.
yes, madam.
Okay, okay. So,
You
so
have to
I
select the minimum value in order to save the cost
yes, yes, yes,
cost point of view.
yes. So I have few problems on UPQC for today. So we'll discuss them, and then in case, okay, fine. So I'll discuss the problems from UPQC. I have selected only few problems for today because I didn't had much time today. If you need any more details, then you can let me know, and I will add those problems in the next session. Okay, let us start. So the first problem for today's discussion is based on UPQC and a single phase circuit. So if a single phase UPQC consisting of D statcom and DVR, so if a single phase UPQC consisting of D statcom and DVR using two voltage source converters with common DC bus capacitor is to be designed for a load of 220 volts. So the load is given in the question as 220 volts and 50 hertz, 22 amperes and 0.8, 0.9 lagging power factor. And in the question, they are using the right hand UPQC. Right hand UPQC P they are using. So right UPQC P is used to provide a reactive power compensation for unity power factor. So this UPQC is serving two purposes. One is unity power factor correction, and another one is voltage regulation at 220 volt 50 hertz across the load. There is a voltage fluctuation. Voltage fluctuation in the system is minus 15%. Okay, so that is a sag with a base value of 220 volts. Calculate the DVR RMS current rating in amperes during the voltage sag condition. Okay, so we are asked to calculate the voltage RMS voltage rating of the DVR. No, sorry, current rating, RMS current rating of the DVR. Okay, so if we just draw a schematic, let us say this is our source, this is our load. Then since this is a right hand shunt compensator, therefore this will be our D statcom and this will be our DVRC. This is DVR, this is D statcom. This is my load, right? Now they have asked me to calculate the current rating of the D statcom. Now after compensation, my current rating will depend on the unity power factor correction that is done by the D statcom. So, in order to calculate the current rating, first I need to find the current in the system, the total power that the load requires. Because after unity power factor correction, only active power will be supplied by the source, right? So, let me calculate the load active power. Let me denote it by PL. It will be given as V. Current is given as 22 amperes and cos phi is given as 0.9. So this will come out to be, this PL will come out to be 4356 watts. Okay. Now, during voltage compensation, what will happen is, during voltage sag, let us say now sag has occurred. Now, because of the occurrence of sag, my supply voltage, let me draw that again. This was my DVR, this is D statcom, this is my load. Now, without DVR and D statcom, my supply voltage Vs was equal to the load voltage. Now, after lagging effect, what is happening is let us say Vs was before some 220 volts. Now Vs dash is, after the occurrence of lag, Vs new is 1 minus 0.15. After 15% lag, it has landed to this value into 220 volts, right? So this will be my value after the sag. This will come out to be around 187 volts. Okay, so this is my sag voltage. Now, during sag, the supply current that will occur will be, so this is my Vs dash. So my Vs dash is the voltage that will occur at this point, right? This is my Vs dash. Now I know the power that the load requires and the current that will flow here. So Is dash will be equal to, okay. Now I know Vs dash and I know my load. So I can calculate the value of the current that will be flowing through the DVR, right? So IS dash is equals to I dVr, which will be equal to my load power divided by Vs dash. So it will come out to be that load power was 4356 watts and Vs dash is 187 volts. So this Is dash will come out to be 23.29 amperes. So the current rating of the DVR of UPQC will be equal to Is dash, which is equals to the supply current after UPQC compensation, which will be equal to 23.29 amperes. Okay. So this was the RMS rating of the DVR. Now let us move on to the next problem. So in the next problem, a single phase UPQC is again considered, and this time the UPQC is consisting again of a D STATCOM and a DVR with a common shared DC bus capacitor, and this time the load is given as 230 volt 50 hertz 0.8 lagging load, and the UPQC that is to be used is right hand UPQC P. The UPQC P is used to provide the reactive power compensation for unity power factor correction at AC mains with a constant voltage regulation at 230 volt 50 hertz. We are asked, okay, there is a voltage sag is given as minus 20% with respect to the base value of 230 volts. Calculate the D-STATCOM RMS current rating in amperes during the voltage sag condition. Now, initially they were asking about the DVR, now they are asking about the D-STATCOM. So, again, it's a right shunt topology. So, again, this will be my DVR, this will be my D-STATCOM, and this is my load. Now I am asked to calculate the D-STATCOM RMS current rating. In order to calculate the RMS current rating of the D-STATCOM, I know that the purpose of my D-STATCOM is to supply the is to take care of the unity power factor correction, right? So my since it is a UPQC P, it can DVR can take care only of active power. That means D-STATCOM has to take care of the reactive power as well as active power. That means D-STATCOM will have two components. So we have already seen that since it's a pointed lagging power factor, it has to take care of the bad part of this current. So that will be called as my reactive part of the D-STATCOM. And for the active part of the D-STATCOM, that will be corresponding to the active power that is flowing through the DVR, which will be corresponding to the SAC component. So let us again start with calculating the load active power component. Let us say load active power is denoted by PL, which is again given as 230 into current is it's 23 amperes. 23 amperes into cos phi is 0.8, which is given as 4232 watts. Okay, this is our load active power. Now, due to voltage sag, my new supply voltage is reduced by 20%. So it will be approximately this, which is 184 volts. Now, corresponding to this supply voltage, my new supply current will be load power by Vs dash. 184 volts, which will come out to be 23 amperes. This is my supply current. Now for power factor correction, uh, now I need to take care of D-STATCOM. What is D-STATCOM doing? D-STATCOM is number one taking care of power factor correction. Okay, so since it is taking care of power factor correction, it will be supplying the I sin phi component of the load. That means reactive power component of my D-STATCOM will be equal to IL sin phi, and that is 23 into zero point 0.6, which will give me 13.8 amperes. This is the reactive part of my D-STATCOM. Now, apart from that, since DVR is supplying active power to the load because it is UPQC P type of UPQC, because of that, another component of current will flow through the D-STATCOM, and that will be called as D-STATCOM A component. And that component will be corresponding to, can be calculated as depending on the DVR rating. So DVR rating is Vs into X. That means since my voltage sag is 20%, so the voltage rating of DVR will be Vs times X, right? It will be 20% of the 230 volts and into Is. So this is the voltage, this is the power rating of the DVR. When I divide this power rating of the DVR with voltage, it will give me the active component of the current that D-STATCOM will supply. So 230 into zero point 0.2 into Is is 23 amperes and Vs is 230 volts again. So this current will come out to be approximately 4.6 amperes. Now total D-STATCOM current will be equal to active component square plus I D-STATCOM reactive power square. So this will be 4.6 square plus 13.8 square. This will come out to be approximately 14.546 amperes.
Madam, why you are not using here IL cos phi, madam? There.
IL cos phi will be the source current, right? That will be supplied by the source. So if this is my circuit, then this path DVR will IS will flow, IL cos phi component will flow through the DVR, but D-STATCOM will supply only I sin phi component, right? So D-STATCOM current will not include I cos phi component, huh? Is it clear?
Madam, here I cos phi here also this come will supply active, madam.
Sorry?
Here the drop is same as the here drop, madam. That's why I'm asking, madam. This
Where
drop
can you please?
across this start come voltage drop across this one and some signal problems, madam. Interconnection.
At this point, you are asking.
Here
Uh,
that bad current I sin phi, madam.
uh-huh.
It will supply to you are also I just become active.
No, no. See, so I sin phi is the reactive part, right? So that is why
Yes, madam. Reactive.
I cos
Here,
phi is the active part and I sin phi is the reactive part.
yes, madam. Here I destat come active means, madam.
So what is happening here is because DVR is present, if it were alone D-STATCOM, then what will happen is my D-STATCOM can only take care of unity power factor correction problem, right? And it will supply only I sin phi component. There will be only one component of D-STATCOM. Now, due to the presence of DVR, my DVR is taking care of voltage regulation. And when DVR is taking care of voltage regulation, it is sharing some, since okay, this is a representation only in the diagram that I have drawn. But in reality, both of these are connected, right? They have a common DC link sharing. Okay, we are talking about single phase, right? So if you look at this circuit, so this common DC link is shared, right? So if my DVR is doing active compensation, then that current also impacts my D statcom. They are not independent. So when I say UPQC P, then active power that UPQC is taking is also flowing through D statcom. This is the closed circuit because they share a common circuit, right? It's not independent of each other. So because of the presence of DVR, and since I am using UPQC-P, this D-STATCOM is having current component corresponding to the active part because my DVR is dealing with active part. Is it clear, sir?
Madam, that interconnection, internet problem is there, madam, today. More internet connection, that connectivity problem.
Okay, so maybe you can check in the YouTube video again.
More internet problem is there, madam, today.
Okay, you can. I will be uploading this video soon, so you can check out then in the video again what I am trying to say. Basically, the thing is that because
Okay,
of the
madam.
presence
Okay,
of
madam.
DVR, this is happening. Okay, they are connected, they are just single unit. And since DVR is dealing with active power, that current, that is impacting my D statcom. So Vs into X is the voltage drop across this DVR, and 23 amperes is the current through the DVR. So the active power, the S rating of the DVR divided by the voltage rating is giving me the active part of the current that is flowing through the D statcom. So this is the apparent power through the D statcom, so through the DVR divided by the voltage. That is giving me the active part of the D statcom current. So let us move on to the next problem for today. So now we are moving to the three-phase circuits. So eh, a three-phase UPQC consisting of D statcom and DVR, again with a shared DC bus capacitor, is to be designed for a load of, so this again the load voltage is 415 volts and 50 hertz, and load is 60 ampere 0.85 lagging, and the UPQC that I have is right hand UPQC Q. This is UPQC Q type. This UPQC Q is used for reactive power compensation for unity power factor correction and voltage regulation at 415 volts. There is a voltage fluctuation of minus 20% again with a base value of 415 volt. Calculate the DVR RMS current rating in amperes during the voltage sag condition. Now, this is similar problem that the first problem that we had dealt, right? Only in three phase. So since it's three phase, the supply phase current, we know that it will be equal to supply line current by root 3, that is 415 volt by root 3, which will come out to be 239.6 volts. Now, load active power will be equal to 3 into V load phase power into I load current into power factor. This will be 3 into 239.6 into load current is given as 60 amperes and power factor is given as 0.85 lagging. This will come out to be 366.58.855 watts, which can be written as 36.659 kilowatt. This is the PL value. Okay. Now, let us see what happens after the voltage sag has occurred. we need to calculate the DVR RMS current rating. So the current after voltage sag will be same as the DVR current rating. So after voltage sagging, my new supply voltage will be 415 into 1 minus 0.2, since 20% is the reduction. So this will come out to be 332 volts. So Vs dash, this is line. So we can calculate phase by 332 by root 3. That will give me 191.68 volts. Now from this I can calculate Is dash, which will be given as PL by 3 times Vs phase dash, which is given by PL is already known to us, that is 36.659 into 10 to the power 3 by 3 into Vs phase dash is 191.68, which is given as 63.75 amperes. This means my IDVR is equals to Is dash, which is equals to 63.75 amperes. Okay, so we just had to take care of, since we know that in DVR, the series current is same as the load current after compensation. So after component, we found the value of Vs dash and we already knew the load power. So we could easily calculate the value of Is dash because our circuit is something like this, right? So I know that load power is flowing and I know that Vs dash is this voltage at this node, and we know that PL is the power flowing here. So I was able to calculate Is dash. That is also similar as the current that is flowing through the DVR, right? So try to draw diagrams and phasors as much as possible so that you get a better understanding of these questions. So let us move on to the next question. So in this question again, there is a three-phase circuit, and for that a three-phase UPQC is used, which is again consisting of both D STATCOM and DVR with a shared DC bus capacitor. And this time the load is given as 400 volts, 50 hertz, 60 kVA load with pointed lagging power factor, and the UPQC that is to be used is right hand UPQC Q is used this time, and it has to provide the unity power factor correction along with voltage regulation at 400 volts 50 hertz across the load, and the voltage fluctuation is given as minus 20% at the base value of 400 volt. So now we are asked to calculate the current rating of the D STATCOM RMS current during the voltage sand condition. Now, since it's a three-phase circuit, we know that the supply phase is given as 400 by root 3, which will be equal to 230.94 volts. And since load is given, we can find out load active power, that is PL, as 60 kVA into 0.8, which will be given as 48 kilowatt. And load reactive power will be 60 kVA into 0.6, which will be given as 36 kVAR. These are the two ratings for the load. Now, for the D STATCOM, after occurrence of sag compensation, let us see what happens after sag compensation. After occurrence of sagging, again Vs dash will be equal to 400 into 1 minus 0.2, since 20% reduction is given. So it will be 320 volts line to line voltage. And Vs dash phase will be equals to 320 by root 3, which will be given as 184.752 volts. Okay. Now we know that the phase load voltage that should have been there for voltage regulation, After voltage regulation, load voltage per phase voltage will be 400 by root 3. That is already calculated as 230.94 volts. And phase load current will be, that is IL phase, will be given as 60,000 by 230.94. 3 V phase I phase, and this power factor will be unity. So after compensation, this will be my load voltage and current, right? So since it is a Q UPQC Q type of UPQC, so the voltage rating of my DVR will be using Pythagoras theorem, load voltage rating minus source voltage rating, which will be equal to 230.94 square minus 230.94 into zero point 0.8 square after 0.2 lagging, 20% lagging. So this DVR voltage rating will come out to be approximately 138.56 volts. Okay. Now we have got the voltage rating of the DVR. Now using the voltage, now I wanted to calculate the D-statcom current, right? And we had just seen that uh, there is this equation for the D-statcom current which has both active and reactive component, and that equation is IL into under root of 1 minus x square plus cos square phi minus 2 cos phi cos of phi minus delta into 1 minus x divided by 1 minus x. So this is the equation. Now we know that we already know phi, which is the power factor angle, that is zero point 0.8 cos phi, and from that we could calculate phi, but we need to calculate delta. So delta is the angle between VL dash and VS dash. So if you look at the phasor, then from phasor we know that tan delta is equals to V dVr by Vs dash, and we had just calculated V dVr and Vs dash is present here. So this will give me 138.56 by 184.752, which will give me 0.75. And using tan inverse 0.75, I can get delta as 36.87 degrees. And now I know that my phi is already cos inverse zero point 0.8, which will again 36.87 degrees. So in this equation, if I'll put all the values that then I'll get that this is this equation will become cos 0 as 1. Okay, yes. So okay, so this will become as this expression. If you solve completely, it will come out to be 0 because all the components will cancel out each other. So you will realize that finally using this expression, D statcom current from the UPQCQ will be 0 amperes. Okay. So this was as in the question, we had to calculate the RMS value of the D statcom current. So here it comes out to be 0 amperes. So that means there is no current flowing through the D-statcom during the voltage sag condition. But there will be other conditions. So that does not mean that we don't need the D-statcom anymore. Okay. So this was our last question for today. If you have any doubts in the questions that we have solved, you could ask right now. Any doubts? Okay, so I am done from my side for today. And in the next session, is there anything that you guys want me to cover from your side? So in your assignment 6, you just have your UPQC questions, okay? Mm. And assignment 7 is not released yet, right? Okay, then I think you will be good to go for your next assignment submission. And in case you have any doubts that were not covered, then you can write to me, and then I will try to respond you there. Okay, guys, then if you don't have any doubts, then we can end today's session.